Hey guys, this video is continuing on with our psychrometric processes. We explored the psychrometric chart and what all of the different variables on it were in a different video. This video I am going to look at what doing a psychrometric process calculation looks like, and I'm actually going to look in specific at the one that we're going to be using for our lab, which is evaporative cooling. So with this, for a psychrometric process, we are going to be thinking about this in our case here using our steady flow energy equation. So our normal form that we're used to of this is going to be our change in energy of our system over time. So this is a flow state. We have equal to the Q dot, the heat in, minus the work being done on it, plus our mass flow rate in, or I should probably put our sum of our mass flow rates in. Oh, that is a terrible sum side. Sum of our mass flow rates in times the enthalpy plus we've got velocity squared over 2. That's our kinetic energy portion plus our potential energy portion. And this is all in. Minus the sum of our mass flow rates out times our enthalpy out plus our velocity out squared over 2 plus our potential energy portion out. So that is our generic energy equation. Now with this, I've said that I have a steady flow. So I'm going to go ahead and make the assumption that I've got no energy. With our psychrometric processes, I don't have any that we're going to be focusing on where we are worried about the control volume. We're going into the control volume. We will have some where there's heat. We're also not going to be worried about any changes in velocity, so no kinetic energy changes. We can assume that those are going to be negligible for most of the things we're going to be looking at, because we're normally looking at HVAC type ideas here. We might need those, but again, remember how large those changes needed to be to impact anything. And then we're not going to worry about potential energy changes because those values continue to be particularly small. So that is our base form of our equation. Now, the difference here, what we're going to run into, is going to be the issue that when we talk about our sum of our m dots, I need to keep track of different m dots now. So I've got different mass flow rates. I'm going to have to break out my mass flow rate of my air. So I'm going to assume that I have one pipe going through. We will have some pieces where we've got mixing going on, in which case we've got multiple airflow rates. But I'm going to consider the case where I have a single pipe where I've got air flowing in, air flowing out, and potentially I have water entering in here, because that's what we're going to need for the lab. Anything else is more of a classroom type discussion at this point. So going in, I'm going to call all of the ins 1, outs 2, and then this is the water. So I have my mass flow rate of air in times the enthalpy of my air in plus the mass flow rate of my vapor in times the enthalpy of my vapor in plus the mass flow rate of any water in times the enthalpy of my water in. I guess this isn't really happening at 1. This is just happening for wherever I'm injecting water into my system. And then my mass flow rates going out, I am going to have pieces at 2. So I've got the mass flow rate of air out times the enthalpy of air going out. And I have my mass flow rate of vapor in that air going out times the enthalpy of my vapor going out. That is my giant equation. Now what I'm going to do with this equation is I'm going to go ahead and simplify it using some terms we have and some things we know. First thing that I'm going to do is I'm going to, instead of just looking at the energy equation, I'm going to look at my conservation of mass. So I've got 2 masses that need to be conserved. So I'll put these guys over here for now. So I have, we'll put it down here. Sum of mass flow rates of air in has got to be equal to the sum of the mass flow rates of air out. I don't want to do a conservation of mass of air and water together, because that would imply that I can have air converting and changing into water and vice versa, which is not going to happen. So from this, I just have my mass flow rate of air at 1 has to be equal to my mass flow rate of air at 2, which I'm just going to call my mass flow rate of air. And the second piece that I have is the sum of the mass flow rates of any vapor / water in has got to be equal to the sum of the mass flow rates of any vapor or water out. So in this case, I have m dot vapor in plus m dot water is going to be equal to m dot vapor out. Again, this is assuming that I have a system that looks like the system I've got up in this upper right-hand corner. We won't necessarily always have that. But what I can do from this is I'm going to actually change this into the form using m dot air to try to simplify my equation a little bit further. So easiest thing to do here is I can say that m dot vapor is going to be equal to omega times m dot air, because omega was my value that was kilograms of water vapor in air per kilograms of air. So this is converting my mass flow rate kilograms of air per second. Kilograms of air cancel. I get kilograms of water per second, which is my m dot v. So I can go ahead and put that guy right here. So I have omega 1 times m dot air. And remember that m dot a1 is equal to m dot a2. So those are the same. I can just write in m dot air. Plus m dot water is going to be equal to omega 2 times m dot air 2. And that means that I can actually solve for this, solve for this m dot of water is going to be equal to the omega out, so omega 2 minus omega 1 times m dot of air. Sorry, because again, m dot air in and out are the same from this equation. Now what I'm going to go ahead and do is I will go ahead and replace those things here. So I'm going to replace this guy. M dot vapor 1 I said was omega 1 times m dot air. M dot air 1 I said was just m dot air. It's the same for both. m dot water. Sometimes I like to replace this in the equation, sometimes I don't. I'm going to go ahead and replace it in this case. Is going to be omega 2 minus omega 1 m dot air. M dot air 2 is just m dot air. And m dot v is going to be my omega 2 times m dot air. Which means that this m dot air can be pulled out of this overall equation. I'm going to leave this while I'm still talking in the semi-generic form, in a little bit more generic form. So I'm going to say, in case I've got multiple inlets or outlets, so I have my q dot plus the sums of my m dot airs in times h air in plus omega in hv in. So that's combining this term and this term. And then I am going to add the sum of my m dot. Okay, so this is the water term, so I'm just gonna leave it as m dot water for now. H water. Know that we could make that blue replacement if we wanted to. So if we've got multiple waters coming in, technically I could also have a term which is the sum of the m dot waters out times the h of water out. And then I also have this last term, which is the sum of m dot air out times my h air out plus omega out hv out. So since I have the potential in this form that I have multiple ins and multiple outs for the air, that's why I didn't use this piece, because this is assuming that I just have one of each. Okay, last simplification we can do here is we can do a simplification for if we are using our tables, because the reason we went through all of this is this term right here is just our big H divided by mass air. That is our enthalpy per unit mass air of our total piece. That is the enthalpy that is specific enthalpy that's showing up right here. So we can make that piece all one equation piece for in, and we can make this entire piece one big piece out. So this form right here, I have assumed one inlet, one exit, one water in. This form right here, I have assumed any number of inlets, any number of outlets, any water in or water out. So that is my very generic equation that I have going on right now. So the system that I would like to specifically talk to you guys about, because this is what you're going to need for lab, is going to be, let me erase some stuff here. Probably should have had 2 slides. Is going to be what we're going to call an evaporative cooler, or common term, a swamp cooler. And the whole idea behind it is we are cooling down air by increasing the humidity. So what our overall system is going to look like is I have a piece here where I have some amount of water, of moist air, going in, some amount of moist air going out, and I have some spray, or I have a wet towel or something that is adding water. So I have water in. And we'll again call this W. So from that, I also am assuming that this is an adiabatic process. So Q, whoops. So my Q here is 0 for adiabatic. And what that means is that my equation becomes 0 is equal to my m dot of air at 1 times, I'll do this in the terms without this green piece first, and I'll add the green piece right below it. So I've got h of my air at 1 plus omega at 1 plus, times my h my vapor at 1. I'm going to do this term second, this last one that I've got written down last year, times m dot air at 2. And honestly, since I have one inlet and one exit for air, the airs have to be the same, both in and out, times h air at 2 plus omega at 2, h vapor at 2. And then I will go ahead and use this form that I had created up top here for my water. So I've got my mass flow rate of water plus the enthalpy of my water in. I'm going to write as plus my omega 2 minus my omega 1 times my mass flow rate of air times my enthalpy of water. And if I wanted to, I could also write this without these m dots, because all of the m dots are m dot air. They're all going to cancel out. So since I do not have a Q, I can go through and I can just cross each of these pieces out, divide the entire thing by the mass flow rate of air, if I so chose. And with this, I have the option to write this, to combine these portions just like I combined them before. So I'm saying 0 is going to be equal to h over ma in minus h over ma out plus omega 2 minus omega 1 times h my enthalpy of specific enthalpy of water. Again, reminding us that these two pieces are from our chart. That's the specific enthalpy given from our chart. So that looks pretty easy. And that is our evaporative cooler here. Some pieces of note for this. As we're working evaporative cooler problems, you will note that omega 1 should always be less than omega 2, because we are adding water to the system, so our mass of water per mass of air is going to go up as we go through the system. However, based off of our definition of our wet bulb temperature at 1 is going to be equal to our wet bulb temperature at 2. So wet bulb temperature, again, is basically if I take a point and I follow it straight up along here, this is what's happening if I am not adding any energy. So I'm more or less not adding much energy. but just adding a amount of water and following this process up. That was the definition of our wet bulb temperature. This is not the same as our dew point temperature. Our dew point temperature is following this line to the left instead of following that diagonal line. I didn't really get into that much. First video, I kind of just talked about wet bulb temperature a little bit and how we measured it. But that's there for you guys too. And that, again, is a big thing we'll talk about in class. So we have these pieces for calculating anything we want here. And then with that, we will notice that in these problems, our enthalpy of our, we'll put it this way, specific enthalpy of our air, of our moist air, at 1 is going to be approximately equal to our specific enthalpy of our moist air at 2, which is to say that these two things are the main players going on here. This value is very small. And we'll actually go through and look at that at the end of our example problem here. So with this, I will do our first example problem looking at our psychrometric chart, just because that is a lot easier. And I have a feeling that most people will stop watching the video afterwards. But then afterwards, we will go through and we will solve it by hand and show that these charts are working wonders for us. So with that, my example problem for us today. I have a system where I have an evaporative cooler, and we'll go ahead and draw out our evaporative cooler here, where I have a state 1 and a state 2, and I have some water going in. And what I know is that at state 1, I have a dry bulb temperature, so temperature 1 is 25 degrees Celsius, and I have a humidity of 20%. And this whole thing is happening at a pressure of 1 atmosphere, just so that we can use my 1 atmosphere psychrometric charts down here. And I want to spray water into the system that's going to evaporate and get pulled out by the system until I drop to a temperature of 15 degrees Celsius. So I'm going to spray moist water into this until that change happens. Okay. So for this, I'm going to go ahead and start by going directly over to my psychrometric chart here, because almost everything I need to do is just following this chart. So initially, I'm told that I have a dry bulb temperature of 25 degrees Celsius down here, and I am told that I have a relative humidity of 20% right here. It is 20%. Yes, I wrote 20%. Okay. So I'm going to go ahead and follow these two lines until they cross and see that it happens right there. Oh, and I should probably put what I want to find. I would like to find the relative humidity at time 2, and I would like to find the mass flow rate of water required to make this happen. How much water do I need to be spraying in that it's evaporating in order to make this happen? Okay, with this, when I am talking about an evaporative cooler, I know that I have my wet bulb temperature is staying the same, and the wet bulb temperatures are these lines right here. So I'm going to be moving along those lines, and I'm going to be moving until a point where I hit 15 degrees Celsius. So creating a diagonal line from this guy, it's approximately going to look like so. and creating my vertical line from my 15 degrees Celsius. It's going to look like so. Considering this is on a screen, that's pretty darn good. Meaning that my final point is going to be right here. So let's make this red. I think that'll be a little bit more visible. So my final point is right here. My initial point is right here. So this is time 1. This is time 2, or inlet and outlet. And what I can do is I can see that time 2 is happening here about halfway between 70 degrees and 80 degrees. So I would say that V2 is pretty easily approximated as about 75% humidity. And then I need to find my mass flow rate of the water. So this is where we actually have to use some calculations from our psych chart. So what we're going to use is we're going to say that we're going to look back at our conservation of mass for our water. So we can say that sum of mass flow rates of water in has got to be equal to the sum of the mass flow rates of water out. Going in, we have the mass flow rate of the vapor at 1, and we have the mass flow rate of our water coming from this little spray piece right here. And exiting, we have our mass flow rate of our vapor at 2. And it occurs to me that I did forget to give you guys something. Throughout this, the mass flow rate of air is going to be 2.5. So what I have this? Sorry, double checking my numbers here. Yes, 2.5 kilograms of air per second. So I am given that value as well. Otherwise, this is an unsolvable problem. I have the mass flow rate of air, and I can change these mass flow rates of vapor to be in terms of air, so I'm going to go ahead and do that. So omega 1 times m dot of air plus mass flow rate of the water is going to be equal to omega 2 times mass flow rate of the air. This is something that we just did on the other slide a second ago. We can say that the mass flow rate of the water is going to be equal to omega 2 minus omega 1 times the mass flow rate of the air. That doesn't make sense. It should be... Nope, no, I had that right. Mass flow rate out minus mass flow rate in is going to be the amount of water that was added to it. So omega 2, for that, I can go ahead and follow this line right here, which hopefully I set up to be at right about 0.008 kilograms of water per kilogram of air, minus my omega 1, which I can follow this guy over, and that is going to be 0.004 kilograms of water per kilogram of air. And I'm going to multiply that whole thing by my 2.5 kilograms of air per second is going to give me a mass flow rate of my water of 0.01 kilograms of water per second. This is an approximate still because I'm using my chart. So 0.01 kilograms of water per second. And one piece before you guys take off to note is that if I look at this specific enthalpy here, my values more or less line up on the same line. So H over mass air at 1 is approximately the same as H over mass air at 2. And really with just our charts, we can't really tell any difference there. Okay, now this next piece is good to know. It's good to be able to understand where everything's coming from, and hopefully will make these problems make a lot more sense when you try to solve them. However, you're probably never going to have to solve it this way, because hopefully you always have the ability to look things up in the psychrometric charts. So if I lose you now, I completely understand. But let's talk about doing this whole thing by hand. So I have exactly the same problem. I want to do it by hand. I want to get as exact of numbers as I can for this. So what does that look like? Well, in order to solve this, we are going to need a couple of things. The first thing we're going to want is we're going to want to figure out what our omega value is. So before we were able to just jump right into our humidity value, our omega values from the chart, we're going to need to find those by hand. I'm going to put it down a little bit because we're going to do something else first. But if you guys recall, our omega value is going to be solvable as 0.622 kilograms of water per kilogram of air times our vapor pressure of our water divided by our total pressure minus our vapor pressure of our water. However, we need this vapor pressure, and how we're going to get that vapor pressure is we're going to use our piece here, our relative humidity, which again, we were just able to use as a line on the graph before. We know from that previous question that our value is 20% for this. And we know from our equations that this is our vapor pressure divided by our saturated vapor pressure. And that saturated vapor pressure is from our charts. So at state 1, I have a temperature of 25 degrees. So this is state 1. And that means that my vapor pressure should be 0.03169 bar. Units of bar up here. So that is going to give us, if I want my vapor pressure at 1, I'm going to take the value for my piece, 20% is going to give me 0.2 times my 0.03169 bar is going to give me a value for my vapor pressure of 0.0063338 bar. And plugging that in down below, I've got 0.622. I'm going to leave out units for space here, times my vapor pressure of 0.006338 bar. Oh, I said I was going to leave out units. Might as well leave out all of them. Divided by, well, I need to change 1 atmosphere into bar, which is 1.01325 bar minus 0.006338 bar. That is going to give me a value of 0.003915, and that is our relative humidity value. So this is kilograms of water per kilograms of air. if we look back above, our humidity ratio, or specific humidity, is, we said, was approximately 0.004. In this case, I've got 0.003915. So that matches up pretty well. Okay, that's the easy part. That is what we did in the previous video. Next thing we're going to do is we are going to go ahead and throw all of this into our big energy problem, conservation of energy problem from above. So we didn't even need this energy problem before. We were able to get away without it. We can't use this one because we don't have this capital H over MA. We don't have the tables for this. So we're going to use this top guy right here. And I am going to write it out with the mass flow rates air because I want to do something with them a little bit here in the future. So I am going to say 0 is going to be equal to my mass flow rate of air times enthalpy of air at 1 plus my omega at 1 times enthalpy of my vapor at 1 minus my mass flow rate of air at 2 times my enthalpy of air at 2 plus omega 2 times my enthalpy of my vapor at 2 plus the mass flow rate of my air times omega 2 minus omega 1 enthalpy of water. Okay, let's go ahead and start filling this guy in. So omega 1 I have. That is 0.003915. That's from right here. That is omega 1. Mass flow rate air is 2.5 kilograms of air per second. We were given that. We need these enthalpy values. So I'm going to do the enthalpy values for the vapor because I have my steam tables here. Again, these are tables taken from the textbook we're using for this class, The Fundamentals of Engineering Thermodynamics, 9th edition. So at time 1, or at my inlet, I'm at 25 degrees Celsius. And my vapor value here, my H vapor, is going to be my value right here. So this guy is at 25 degrees Celsius. I have a value of 2,547.2. And that is in kilojoules per kilogram water. That's why we need this omega to convert it to per kilogram air. And my H vapor 2 here is going to be same thing, except at state 2 we are at 15 degrees. So at state 2 I'm going to grab this value right here, which is 2,528.9 kilojoules of energy per kilograms of water, again converting. And then my H's of air, I'm going to go down to my next slide here. And I unfortunately have to work in Kelvin. All the temperatures in this graph are in Kelvin. So I have, at state 1, I am at 25 degrees Celsius, which is going to be 298.15 Kelvin. So 298.15 is going to be between 295 and 300. If I do a linear interpolation between these two H values, I get H at 1 of 298.3326 kilojoules per kilogram. Again, I probably would round earlier, but I'm specifically doing this in order to have a comparison for you guys so that we can, actually compare this to our other values and get an idea for it. Our second temperature is at 15 degrees Celsius, which is going to be 288.15 Kelvin. So H2 is going to be, we're going to take a value between 285 and 290. We're going to take these two values and interpolate them, and that gives me a value of 288.3428 kilojoules per kilogram air. So I'm going to go ahead and pull those numbers up top here. I have a value of 298.3326. I'm going to leave it as 2 decimals for space here. Know that I didn't do any rounding in my calculator, just when writing them down. So the numbers I'm listing out are actually not even as accurate as the numbers that I put into this. And then for HA2, I've got 288.34. Omega 2, I don't know, and that is my only unknown. That's what I'm trying to solve for. Mass flow rate of air is still 2.5. Mass flow rate of air is still 2.5. Omega 2 is still what I'm trying to solve for. That's the same omega 2 as we saw earlier. Omega 1 is this value from right above here of 0.003915. And the enthalpy of our water, we weren't given a ton of information about this. We're going to go ahead and assume that the temperature of our water is the temperature of our water at our 25 degrees Celsius initial. So we're going to go ahead and grab the saturated enthalpy of our water, assuming that it's not changing much from the saturated value, even though it's probably not at the saturated water state. We will grab this because it's what we have, of 104.89 kilojoules per kilogram water. And that is all of our values. The only thing that we don't know is we have those 2 omega 2s that we do not know. So with that, I can go ahead and start solving. This portion right here is going to come out to 2.5 kilograms per second times 308.3053 kilojoules per kilogram. Again, these are both kilograms air, which comes out to a value of 770.76 kilojoules per second. If I just drop this piece down here, so I've got m dot air times the enthalpy of air at time 2. This is going to give me a value of, why do I not have this? I've got a negative sign in front of this because this is energy leaving the system. So I have a negative 720.857 kilojoules per second. I then take this portion, so I've got m dot air times omega 2 times h enthalpy of the vapor at time 2. I don't know omega 2, so I get a value of negative 6,322.25 times omega 2. And then my water for this first portion, I don't know, so I just have m dot of air times omega 2 times h enthalpy of the liquid water, and I get a value of positive 262.225 times omega 2. And then for this last portion, writing all over my graph here, but I have a value of negative 1.02666 kilojoules per second. Moving my omegas to the opposite side and simplifying, I get that my equation comes out to 48.8797 kilojoules per second is equal to 60.025, and that is going to be what are the units of that at this point? So I've got kilograms air per second times my kilojoules per kilogram water. So, this is yucky units. Kilojoules times, it's disgusting units. I'm not going to write it all up. Times omega 2, and that will eventually be, if I include that omega 2, I'm in kilojoules per second. Okay, which means that my omega 2 comes out, and that omega 2 is 0.008066 kilograms of water per kilogram of air, and that is my omega 2. I didn't actually ask for that one, but I can still compare it. So in this case, I had omega 2 of 0.008, which is what I found in my graph. That's my humidity ratio again. I like calling it omega. I apologize. But 0.008066 is pretty darn close to that. But this was a whole lot more work to get there. With that, that is not what I asked for. I asked for my I asked for my phi, which is my relative humidity. It's getting late. I apologize. Terminology is failing me. So I would like phi. In this case, I know that in order to get phi is going to be equal to my PV over my P set, which is what I have right up here for it. I need to get my my partial pressure of the vapor in order to get there, and I'm going to do it basically in the opposite order as I did before. I'm going to use my relative humidity to get there. My humidity ratio. Yeah, humidity ratio. I got the term right that time. Okay, so omega 2 is going to be equal to 0.622 kilograms water per kilogram air times my partial vapor pressure at 2 divided by my total pressure minus my partial vapor pressure at 2. I want this PV2 term. I have my pressure. I have my omega 2. This is going to turn into my partial vapor pressure at 2 is going to be a humidity ratio at 2 times my pressure divided by 0.622 plus omega 2. So that gives me a value of, 0.008066 times 1.01325 divided by 0.622 plus 0.008066 is going to give me a value of 0.01297 bar, because I put this value in bar. That'll give me a value out in bar. So with that, phi is going to be my PV2 divided by my saturated pressure. My saturated pressure at this point, I'm now at my 15 degrees Celsius, so I'm going to use a different value than I used before. So I have 0.01297 bar divided by 0.01705 bar, which is going to give me a value of 0.76078 or 76.08%. And if I compare that 76.08%, before I was between 70 and 80% relative humidity. I kind of guessed it was 75 because it looks about halfway in between there. It's actually 76. I'd say that's pretty darn good. Okay. One last thing is finding this mass flow rate of the water. So we'll go ahead and do that to finish up. Again, hopefully you're seeing that this is a much slower process than it would have been if we just used the charts. So I have a conservation of mass, same thing that I did above, same piece that I did here. I'm just going to go ahead and do it with my slightly more accurate, significantly more painful numbers. So conservation of mass, I've got the amount of vapor going in plus the amount of water going in is going to be equal to the amount of vapor going out. So my mass flow rate of the water is going to be equal to the mass flow rate of the air times these two humidity ratios. So that's going to be 2.5 kilograms of air per second times 0.008066, and that is kilograms of water per kilogram of air minus 0.003 915 kilograms water per kilogram air, which gives me a mass flow rate of my water of 0.01038 kilograms per second. That's kilograms water per second. Couple things here. Those two values, I took the omega value that I found right here, and I took the omega value that I found right here, and those are the two pieces that went here and here in my equation. And then that 0.01, look at that. It is very similar to what I got from just my 2-minute calculation using the psychrometric charts. So mass flow rates staying the same. Okay, last piece here. I talked a little bit in this how my specific enthalpy for my moist air is more or less the same. And if I go back to this, here is my overall equation. So if I look at these values, this guy is my, let's get a different color here so that it's a little bit more visible what I'm trying to do. This guy right here, oops, that is H over MA for state 1. This guy right here, this guy is H over MA for state 2. And that means this guy right here is the difference between those. So H divided by MA at state 1 minus, so this is actually going to be the other way around. At state 2, did I get that backwards? No. Yeah, state 2 minus H divided by MA at state 1 is, wrong way, is going to be equal to, sorry, I did this with my mass flow rates originally. I'm going to do this without it in this case. It's H2 minus H1. Yep, H2 minus H1 is going to be equal to omega 2 minus omega 1 times HW. Omega 2 minus omega 1 times HW is going to be those differences, because I've divided everything here by my mass flow rate of the air, by that 2.5. So with that, my omega at 2 was 0.008066. My mass flow rate at 1 was 0.003915. And my enthalpy of my water was right here, my 104.89. 104.89. This is going to give me a value in kilojoules per kilogram air. And I need to grab a calculator quick, and I can plug that in. That gives me a value of 0.4353 kilojoules per kilogram air. Now, I could go through and I could plug in, I had originally plugged in for each of these individual pieces right here and compare the size of them. What I'm going to do is I'm just going to compare it to the values I'm seeing in my chart. And the value I'm seeing in my chart is right here, which is going to be 35 kilojoules per kilogram dry air. And I would say that this guy is much, much less than 35 kilojoules per kilogram air. So they That is just showing how really insignificant this change in energy. The amount of energy of the water that's being absorbed is significantly less than the amount of energy in our air, in our vapor state, and in our gas state. So, something to think about there. When we go all the way back and we talk about our system here, where I said it was very small, it is very small because this was like 0.4, this was about 35, this was about 35. So, okay. Sorry it was so long. Hopefully that was helpful. Take care.